Testing, testing, 1, 2, 3, testing, testing, hello, hello. Okay, hello everybody. Welcome back. What? There we go. Okay. No, don't click that. Okay. Stop that. Okay. Okay. Sorry about that, folks. Yes, hello. Welcome back. Hope that everybody had a good week, that they were hypothetically having off, but probably you just did a lot of homework. I know that's kind of what happened with me. Good morning to everyone in the chat. Yeah, it's, I have to say, at this point in time, that, one of the things that occupied me during my reading week is that on Thursday I had my wisdom teeth removed, and that was not a lot of fun. But, you know, one of those things that you have to do. I wouldn't recommend that for a recreational pursuit, by the way. But if I seem a little low energy right now, it's because my mouth is still full of stitches, actually. So if I'm not, you know, giving you the exaggerated hand movements that I normally accompany the lectures with, it's because I'm still feeling a bit. But we'll try to plug our way through the lecture anyway. Who knows? Maybe if I'm a little low energy, we might actually get more progress made. Went back to high school and graduated. Wow, that's cool. I didn't even know you could do that in a week. That's awesome. So, you will definitely be tested on the video on Avenue. Absolutely. That's a joke. You're not going to be tested on it. If it doesn't, I'm not going to spoil the joke for anybody who hasn't seen it yet. Anyway, so check under Reading Week on the course content for the video I'm talking about. It's just a little bit funny. Anyway, I'm a professor who likes to occasionally inflict outdated practical jokes upon his class. Anyway, so there is one thing that we got to talk about, sort of, before we get into any of the course content, and we are behind in the course content, so I need to move through this reasonably quickly. But a situation developed over the reading week where a colleague of yours, whom I shall not reveal the identity of, anonymously posted to Piazza that basically this individual took a look at the test cases that we were using in order to run the auto-grading software and said, I wonder if this is a vulnerability in these test cases, and wrote a small program which actually works to completely disrupt the manner in which the test cases on Jupyter actually evaluate your work. I'll probably talk about this when we get it in a little more detail, because when we get into classes, because it's a clever use of some of the properties of classes in order to modify certain things that are necessary to evaluate the return results of your functions. So this clever little solution that completely breaks and destroys the autograder. And by breaks and destroys, I mean can be used to cheat any question. All you would have to do is put this piece of code in the answer cell and hook it up to the function in a very superficial manner, and it would pass any test case, basically. Well, pass, shall we say, a very large portion of the test cases that would be applied. Because of, well, essentially, it's not even necessarily a problem that this vulnerability was found. Like, the mere fact of this vulnerability being found isn't necessarily a problem. The problem was that this individual made the oversight of publicly posting it, which I imagine this will have, made the rounds through the certain dark, seedy underbellies of the internet, as these things tend to do. So this is requiring a response, not only on our part. We'll see. I've been in contact with people in the department who will have a better idea of how widely this information needs, like the fix needs to be disseminated, but we're working on a fix for it. The person who found the vulnerability themselves has been helping us to develop a counter strategy to it, which we appreciate. And basically at some point there's going to be a big update to all of the test cases, because basically from our perspective and the grade team, what this means is that we have to go through every single test case and every single assignment and rework it so that it's no longer demonstrates this vulnerability. Unfortunately, this has basically exposed two vulnerabilities. However, the first vulnerability that it has exposed is the one that your colleague found the exploit for, and the other vulnerability, is that we show you guys the code that's used to mark your assignments at all. The more and more we've been digging into this problem, the more it has become increasingly obvious to me that anybody with a sufficiently advanced level of Python can come up with some way of cheating the autograder. To some degree... Oop. Okay. That's just my wife's cell phone went off. So anybody with a sufficiently advanced knowledge of Python can find an exploit in what we're doing. So, unless we can come up with a solution that we can guarantee to be completely uncrackable, which I don't believe is possible at this point in time, it's not going to be prudent or advisable for us to release the code that is used to mark your assignments. This means less feedback, basically. We're going to see how satisfactory it is for us to release solutions to the various assessments after they've been collected, so that you can compare your answer to the hypothetically correct answer. Hopefully that's sufficient in order to hopefully that's enough information that you guys are still having a good learning experience. But the practice of revealing to you guys the code that is used to mark your assignments it has been revealed to be a security vulnerability, and it's no longer going to be the case that we do that. That's sort of, I guess, in some sense unfortunate, but that's how it goes. I'm going to just try refreshing this chat to see if you guys are actually saying anything. You guys aren't actually saying anything. Okay. Oh, there we go. Does it say that it's due February 16th? That will be a bit that was left in from a previous offering of the course. Assignment 4 will be due at the end of this week, I believe. Yeah. For the official stance on when things are due and that sort of thing, please consult the course syllabus. Yeah, so yeah, assignment 4 is due at the end of this week. So there you go. So yeah, the tone of this announcement is somewhat ticked off, I would say. Is the volume really low? Let me turn up the volume a little bit then. Hello, 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 hello. Testing, 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 testing. It's probably just because I'm speaking more quietly because my voice, you know, my mouth doesn't feel great at the moment, so I'm probably just speaking lower than I usually do. But thank you. And if anybody has any other, technical comments related to the stream, please let me know. Like, if the audio desyncs again, I can fix it. Like, I can fix stuff. I just need to know what's happening, because I'm not actually listening to this at the time that I'm doing it, because that would be almost impossible to actually do a lecture. Okay. All right. So, this is all true. So why don't we get back into our lecture material so that we can continue our merry journey through the land of Python. So, back before the break, we were talking about scoping. There are a few slides on scoping. I'm not sure I'm going to go through them in a huge amount of detail because, basically we were supposed to be done all of these topics before the end of last week, and this is like almost a week's worth of lectures right here. So if we don't get the lead out, you guys are going to start getting too behind the assignment material. So scoping, roughly speaking, you've got global variables and local variables. Local variables are only available in the function they are defined in, and global variables are available to the main program and to all functions contained in the main program. So you may consider the scope of a variable the places in the program where it can be accessed correctly, or it can be used or referenced. So if you have this situation where you're just declaring variables in main execution, of course, in Python is defined as anything that's not inside of a function. This reduces the amount of reuse that your code can see, and it definitely drastically reduces the amount of modularity that you can use. You notice if for example we were to define a function definition in here, we would have both n and x available. In this situation, however, these are local variables. Notice that the argument to a function is considered local to that function. You may have noticed that arguments that you provide to a function are only applicable inside of that function. means that the scope is local to that function. So, this is all true. So there's a slight error in the slides here, which I've never quite had the opportunity to correct, which is that the scope of I is only defined for the inside of the for loop. That's not actually true in Python, although it is true in C. C being a language that's much closer to the hardware than Python. It's a lower level language. Python is a C-based language, but if you use for I in range of 10, for example, do whatever, you can still access the value of value of the index, the value of I, once that for loop has been terminated. So that's a slight difference. But you'll notice that if you try to execute the code that's on this slide, if you try to access the values of x and n outside of the function definition itself, you'll notice that you actually get an error. So if we try that, let's say y is equal to 3, return x plus y, just some simple little function. And then we run it on 7, sure. If we try to access the value of y, you'll notice that we get a name error. Name error, name y is not defined. Y does not exist in the global context. So, an important component of understanding the idea of scope is to understand the contexts in which a variable exists. If you end up studying a programming language like C, we think of the idea of where a variable exists in a very concrete and real sense, because we get involved in how the computer manages the memory, how that computer keeps track of what variables exist and when. During a function call, there's this is a little bit of a tangent, I won't go too long on it, but there's a part of your memory that keeps track of the function calls that have been invoked. And some types of variables, in particular automatic local variables, if that would be how it's referred to in C, in most other languages just local variables, these are stored inside of the structure that keeps track of the function calls themselves, which is called the stack, or the function call stack, or just the call stack. When a function terminates, that section of the stack is released. The memory is no longer associated with any data. So any variables that are contained inside of that stack frame, that's what they call it, a stack frame, those are also released. They are deleted. They no longer exist. The reason that local variables are not accessible outside of the function in which they exist is because they literally, physically do not exist in memory outside of that function being called. That's how the computer works. Hopefully that's not too out there. Let me check for questions. Boop. Can we have a bonus if we find an efficient way for Autograder? I think we're going to try to minimize student involvement in the development of auto-grading software from here on out. Although oh, didn't we do all of this already last class? We were about to start recursion. Were we? Okay. Did we do the software design stuff? Oh my goodness, I'm so sorry. Yeah, we did. Oh my goodness. Well, at least we only lost 10 minutes. Thank you, Tess. Or Tracy. That's Tracy, not Tess. Thank you. Sorry about that, folks. Well, maybe I explained it slightly differently. Alright, so let's talk about recursion. Although I guess I'll go through the rest of it very quickly. Scoping, scoping, scoping. Scoping is important. Modularity, modules. Modules good. Decomposition good. Abstraction good. Abstraction, modularity, essential for the development of large and complicated programs. If you don't have correct abstraction techniques, then you won't be able to write them. You can document your functions using doc strings. Doc strings are enclosed in triple quotes. This is also what Python considers to be a multi-line comment, even though it's technically not a multi-line comment. It's a documentation string. And you can access documentation strings from the Python interpreter by just putting the function inside of the putting the function name as the argument to the help function. That'll display whatever is contained in the doc string, including stuff that you write yourself. Press Q to quit. So there you go. So let's talk about recursion. You may remember that we were talking about recursion. We were talking about we covered recursion from an abstract conceptual level previously in the class. We were talking about the factorial example. Of course, the factorial is defined it can be defined with a smaller factorial inside of its definition. This is not the only way to define factorial. You can also define it with like the big pi notation, which is similar to the big sigma, except it uses multiplication instead of summation. However, one way of defining factorial is to say if this n is equal to 0, then we return a 1, and if this n is greater than 0, then the definition of each term in the factorial is n multiplied by n minus 1 factorial. So, very roughly speaking, a recursive function is a function which calls itself. So, because this definition of factorial contains within itself a smaller, you could think of this as invoking the factorial function again, but with a smaller value. This is the essence of what it means to be recursive. In terms of the nomenclature, we call the top one to be the base case, because there's no further invocation of factorial that's necessary in order to find the value in this particular case. Because it does not require any further function calls, you can think of it as being the case that stops the recursion. So, how recursion works functionally within the context of the computer is you have a function call. That function call invokes a function call. That function call invokes another function call, and so the function keeps calling itself and calling itself and calling itself until it hits some case where it doesn't have to call itself. Then that calling of the function returns some concrete value to the thing that called it. That generates a concrete value which is returned to the thing that calls it. And so you get this cascading effect where the returned value is brought down and 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 down all the way through all of the function calls that were generated until it eventually reaches the original call to the recursive function and returns the value that is the correct value for that function to return. So, if we were to express the factorial function in Python, in our handy-dandy Python interpreter, we would do it something like this. If n is equal to 0, return 1. Else if n is greater than 0, return n multiplied by factorial of n minus 1. So it's very, very important that you don't just return n to the factorial function. It's very important that you have the n minus 1 here. Not only because, that's the actual definition of the function, but because if you were to have a function recursively call itself and provide the exact same arguments that it was provided, what you end up with is the equivalent in recursion of an infinite loop. You would end up with an infinite recursion because the input value is not moving one way or the other. You would never eventually hit this base case. You would never hit this guy. You would always be executing this guy. So, factorial of 5. There you go. So let's examine this function a little more and put some print statements in it. So, n is equal to, and then we will print the value of n. Or let's say calling fac with n equals that. Good. So you can see the first call that we get is we're calling this function with n is equal to 5. Then 4, 3, 2, 1, and 0. When we have 0, then we get the answer because it's been passed back up through the subsequent function calls. So, notice that the number is decreasing down to the base case. So the number is traveling in the direction of the base case. But here's a question. What happens if we start with a negative number? Like negative 10? Because neither of these cases hit that, right? Well, the function in this case doesn't actually return anything if n is equal to negative 10. Hypothetically, you may want to insert code something like raising a value error. We're going to get into how to raise errors in a little bit in this course. But if you have a recursive function or any other function that has the possibility of going into an infinite loop for particular inputs, and that's unavoidable, it's often a good idea to make that into a case that raises an exception, creates your own error. So there you go. This is more or less what we did. So the n equals 0 case is the base case, and notice that in this case they use else instead of using n is greater than or equal to 0. That means if you configure the function in that manner, then if you provide it with a negative value, then it will continue to it'll do the thing that we said I really should define these in a separate file and load it separately. But, you know. So, this is more or less what I've demonstrated, except it's sort of, oh my god. It calculates the value of the recursive call, it prints it, and then returns n times that, which is basically the only difference. So, if we invoke this function as it stands, we get something similar to what we just demonstrated, except it indicates when it's returning the base case, so, and when it's returning from each of the iterative cases. So, the first one that is the first call of this function that returns a concrete value is, of course, the base case, as I had demonstrated. So, let me see if people have questions. Yeah, oh, sorry, yeah. So, factorial is defined as all of the numbers up to the number you're taking the factorial of multiplied together. You guys should, if you guys did high school math, you guys should have seen this when you guys did permutations. It's from combinatorics. Okay. So, strictly within the definition of factorial, negative numbers aren't actually strictly allowed. You actually have a factorial button on your Casio calculators. If you take a look at, yeah, it's x to the negative 1. I'm not sure if you guys can see that, but it's the x to the negative 1 button. If you shift and hit that, that's actually a factorial function that you have built into your calculator. I mean, hypothetically, you could use pop to reverse a string, but it's much easier to just do this one. There's also a dedicated reverse function. Yeah, that's the mathematically precise way to say it. Is that the negative integers are not in the domain of the factorial in the same manner that decimals, like it's not an operation on rational numbers either. It is an operation on the natural numbers. And it is actually 0 factorial is defined as 1, despite the fact that, you know, hypothetically, if you were to take the strict definition and multiply 0 times the entire list, you'd get 0 every time. But yeah, anyway, there you go. We're back to math already. So, every time we recurse, recurse is the verb. It's the verb form of recursion. Every time we recurse, the interpreter creates a new scope for the variables in the function. So recursion is so what does that mean? It means that, so you can think of all of these nested function calls as being a series of increasingly local scopes. So whenever you use a variable name inside of a function, it automatically defaults to the most local existing value of that function, right? So let's say we had some variable n that was equal to 10. Let's go back to our example up there with define function, right? So if we defined y as being equal to 20, and we defined, remember our definition of func is y equals 3, return x plus y. If we then invoke function on 10, we get 13. When, if you assume that it would take this value of 20 instead of this value of 3, your expected return value would have been 30, not 13. So despite the fact that the variables, despite the fact that you're working with one name, you are working with two scopes, and each scope has its own distinct version of that variable. The function, or any function, will always refer to the most local version of the variable, or the most local thing named the thing that you're trying to use, in order to actually perform its calculations, unless you've specified explicitly that you want the global version in this particular instance. So that's a common pitfall when you're trying to use global variables. Incidentally, the use of global variables is a thing that's much to be discouraged because it decreases modularity. So recursion is a natural technique for solving problems with an inductive structure. Inductive structure just means that you have things defined in terms of a base case and an iterative case. Depending on the structure of the program, recursion can be an inefficient solution. So let's talk about the Fibonacci sequence. So with the Fibonacci sequence, pardon me, you can see, if you know about the Fibonacci sequence, you'll know that each term in the Fibonacci sequence is defined as the sum of the previous two terms, unless you're talking about the first two terms in the sequence, in which case both of those are 1. So it's 1, 1, 2, 3, 5, etc., etc. So the recursive definition of the Fibonacci sequence involves two calls to Fibonacci. One, the previous element and the element before that. This would be the base case. The top one would be the base case, and the bottom one would be the iterative case. So let's do our naive interpretation of the Fibonacci sequence. And let's do this in such a manner as the code can be easily modified post-fact, shall we? Fib.py. Boop. 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 Okay. So definition. Fibonacci. Fibonacci of n. If we take a look at our definition over here, we wish to, in the case that n is equal to 0 or n is equal to 1, we wish to return 1. Otherwise, we return the, let's just separate it out. It doesn't have to be separated out like this, but, you know, I'm doing it because it might make it easier to show that how things are working a little later on. So, then we want to return f1 plus f2. Okay, then, now let's call the Fibonacci number of 5. Now, I'm just going to execute this in terminal. Sorry, it's not in dark mode, everybody. Python 3 fib.py. Oh, it doesn't actually return anything. There. So the Fibonacci the fifth Fibonacci number is 8. If we wanted the 10th. But here's an interesting thing. This is a thing you can do in Linux. So you can time your executions to see how long they're taking, right? So for 10, we've got a system time of 0 seconds. How about 20? There we go. You can see that whereas before we took basically 0 milliseconds of system time to perform the calculation, we now take 12 milliseconds, and we've doubled the number. So let's try 30. How long do we think this is going to take? Ooh, come on. You can see the numbers are getting big. You could notice how the lag there. Oh, I'm sorry, the real time. So, yeah, so you can see that that took a whole half second to process. That one took half of a tenth of a second to process. So, let's see what 31 does. So, 31 hits 0.8 seconds. 32, you can see, like, it's noticeably lagging now. We're now hitting 1.2 seconds. So you can see that, and, you know, this isn't just because my computer is old. We're now close to 2 seconds. The relationship between this number and the runtime is pretty extreme. Computers these days are really frigging fast, and for this code to take this long to execute means that this code is being run a very, very large number of times. So we're going to examine why on earth that would be happening. Let me check chat for a second. Oh, that's a good question. So, referring to the factorial question, how is it that we are going from 4 to 5 to 4 to 3 to 2 to 1 to 0 without having a counter? It seems like we're looping without a loop statement. That is actually a very accurate way of describing the situation. You can think of recursion as looping without having to use a loop. That is a good way to think about it. The reason that we don't need a counter is because we're keeping track of the information that the counter variable would be keeping track of within the context of the arguments to the functions themselves. So we don't actually need one. But yeah. Yeah, so if you're in computer science and you're taking the course on Haskell, Haskell is a language that doesn't actually contain loops, at least not in the conventional sense. Where in Python you use a for loop, in Haskell you use tail recursion, which is a more specific type of recursion. Yeah. You can basically only use recursion in Haskell. So all of this going on about recursion is mostly for the benefit of the people who aren't in computer science, to be honest. Which language is easier? Python is easier than Haskell. Which language is more powerful? Haskell is more powerful than Python, because it has more math. It has a higher degree of mathematical abstraction. But we're getting a little off topic. So we know that our naive implementation works, but not efficiently, because we can only get to about 30 or so before we start running into extremely long runtimes of whole seconds. And I know, like in some contexts, a runtime of whole seconds isn't that extreme, but the thing to keep in mind, if you're following the progression of this, it's like a 1.5 multiplier on the runtime for each additional number that we go up in the argument. So you can imagine if I were to, at that point, like at the point we are, suddenly jump by 20, we would definitely be looking at a runtime of, hours, which is dumb. We can do things more efficiently. So let's modify our Fibonacci function just slightly to be able to reveal how many times our function is being called. Let's do this with a global variable. Mostly for the purposes of debugging. So global counter. Oh my gosh, my semicolon reflex is kicking in again. Counter plus equals 1. We then set the counter is equal to 0 in main execution before the function call. We call Fibonacci, let's pick something reasonable like 10 or 20. Now let's print the value of the counter. How many times is Fibonacci, how many recursive calls to Fibonacci do we make if the counter, if we invoke it for the number 20? You can see we actually have 21,891 invocations of fib when we only want to calculate the value of 20. And it's like, what? Why on earth would that be happening? That seems like a lot. I'm going to skip this question because I'm doing my own thing. So the answer to that is it's all to do with the fact that for each recursive call, for each iterative step, we are actually creating two separate calls to Fibonacci. Because there are two separate calls occurring each time, and you basically double the number of recursive calls that you need every time you increase the value of the every time you increase the argument by 1. So for example, if I was to go for 21 here, notice that we've gone from 21,000 to 35. And you'll also, if you've been paying attention, you'll notice that's just about exactly the same ratio as the runtime increases by. I wonder why that happens. Maybe they're related. So the number of recursive calls that we're making is dependent, it's dependent on the size of the argument. And the relationship between it is roughly one of doubling. This is bad. Generally speaking, in computing, we consider that to be a bad property because it means that the computer can unexpectedly fall into cases that take days, weeks, months, or even years to execute. Generally speaking, if your program is going to take a month to execute and it's not the 60s, then you should think about optimizing optimizing your program a little bit. And we're going to talk about an optimization to it. So you'll notice, and we're demonstrating here how the counter is increasing with increasing n. So for n is equal to 4, we get a counter value of 9, 6, 25, 8, 67, and 10, 177. And we can reproduce those with our code that we wrote as well, just to demonstrate that. 177. So there you go. A purely recursive solution to computing the Fibonacci sequence is inefficient because it has to recompute the same value many times. So we are going to use an advanced algorithmic technique called dynamic programming in order to save ourselves effort. So the interesting observation that we can make about this whole situation is, sure, when n is equal to 20, we have 22,000 different invocations of Fibonacci that occur, but there are certainly not 22,000 unique values between 0 and 20. That's obviously not the case. So what the computer is actually doing is every time it invokes, for example, in this case, fib2, it has to recompute it completely from scratch because it's not saving intermediate values, not automatically. You, as the algorithm designer, get to have that fun. So next time in class, we're going to talk about a solution to the Fibonacci problem that saves intermediate values and thereby drastically reduces the amount of runtime that it takes to calculate the Fibonacci number. I'm going to take some questions, and then we'll let you guys get on with your day. Yes. Yeah, actually, so it's actually pretty easy to crash. It's pretty easy to crash a Python program. Well, you don't crash it. You produce an exception, which you can then handle. But like our factorial number, right? If you have a sufficiently large number, you'll just crash that outright as well. Maximum recursion depth exceeded while calling a Python object. So in Python, if you try to ask for more recursion depth than the Python interpreter is sort of default set to, you'll enter into you'll create an exception. In Haskell, you don't have to worry about that because recursion is like the primary operation in Haskell. It's been optimized so that it never like runs out of recursion space, but Python will. Python is the jack of all trades, master of none. Yeah, I guess you could say that. Why is Haskell more powerful than Python? Because you can say less, you can say more in less space. That's a good sort of baseline. The mathematical abstractions that Haskell uses are a lot more powerful than the ones used in Python. Python is a it's a C-based language. As much as it likes to dress itself up, it is fundamentally an imperative language, whereas Haskell is a functional language. It's in terms of its actual syntactic expression, it's much more close to like the mathematics that the algebra that you would write down on a piece of paper than the type of programming we're doing here in Python. So it's more powerful because it can express more things in less space more correctly and with less debugging than something like Python. But yeah. Cool. Why use recursion over a loop? For some problem definitions, recursion is a natural solution. Some algorithms are just naturally more amenable to recursion. So it's kind of like I had a math professor who once said in class something I'll never forget. He said, "Sometimes it's possible if you're faced itches. It is possible to scratch your face like this, but it might be more easy to scratch your face like this. And that's kind of the situation that you're in with recursion. It's a different tool that has different things it's good for. You'll find this is also a thing that's the case with programming languages in general. Some programming languages are better at solving some types of problems than other programming languages. It's totally possible to manage a database using Haskell, even without using SQL libraries that I'm sure exist with Haskell. But it might be easier to use SQL. Oh, you've managed to get Stack Overflow in Haskell? That's very talented of you. But yeah, so that's why you would use... It's kind of a similar question to why would you use a for loop rather than a while loop. Sometimes it's a better solution to the problem. You have to think of these programming language constructs as... they're all tools in your tool belt, right? A programming problem is like a problem with a house. If your plumbing is leaking, you might want to use a monkey wrench rather than a ball peen hammer. Yeah. Anyway, hopefully that's an answer to your question. Stack Overflow is... Yeah, so Stack Overflow occurs because the system stack itself is limited, because the size of the memory on your system is limited by the number of RAM chips that you have, for example. So obviously, there's a point at which your computer just runs out of space for all these function calls. However, that's, typically very large. You despise Haskell. I hope that you can learn to love it eventually. When I was first entering grad school, I had a class where I had to do a project in Haskell, and I kind of fell in love with Haskell in grad school. So I have my own opinions about Haskell, and when it is correct for it to be taught. That the approach that the department has decided to take with introducing Haskell as early as it is being introduced for you guys is that it's sort of the effort is to try to prevent bad coding habits before they take root, because there are certain bad habits that you pick up from coding in something like Python, like using global variables. You aren't necessarily thinking about programming in as rigorously in a rigorous mathematical manner. So because the problem with Haskell is, in order to do anything in Haskell, you have to be thinking in a more rigorous mathematical manner, because if you're not, then your code is just going to get barfed back up by the compiler. So the whole point of trying to introduce you guys to Haskell at this point in time is to try to get you thinking in a more mathematically rigorous fashion about programming and about algorithms and design and that sort of thing. So I understand where the department is coming from. I also totally get that Haskell is a difficult language, and it's kind of, to some degree, throwing you guys into the lake and expecting you to sink or swim. But, yeah. Ooh, they taught you C in high school. That's good. C is an excellent language. as I've been teaching this C course as well, right? And with this C course, it's like I remember now why I liked C so much. It's like you really do have access to so much of the computer in C. It's just it's a pleasure. It's like wrestling with God. I don't know. That's a weird way to say it. Anyway, this reasoning is also why discrete math is a first-year course now. Yeah. So my my impression of some of the the changes that have occurred to the first year comp sci, to the sort of comp sci organization in general, is to make you guys, to give you guys sort of resume-able skills earlier on in your degree program so that you have access to co-ops a year earlier. That was a big selling point, I think. At least that's what Dr. Call was talking about during the that presentation at the beginning of the semester that maybe some of you didn't attend. I did, though, so you didn't have to. Wah, wah, wah. But yeah, so I know a lot's gotten thrown at you, and hopefully you guys can manage it, but yeah. Mathematically rigorous thinking. Introduction to algorithms. These types of algorithms questions are very often the type that end up on interview questions, as it turns out. You know, like, what's a stack? And stuff like that. But yeah, I hope you guys can sort of accept that, you know, you're in good hands with respect to the design of your program. Anyway, yeah, so I've been waffling on long enough. Thank you very much for listening to me speaking today. Hopefully next time my mouth will be a little more healed, and I will be able to speak somewhat more rigorously to you guys and be a little more excited about things. Take her easy, folks. I'll see you tomorrow.